Today is one more lecture on the biochemistry of senses, so there is something in between the biochemistry and neurobiology. So maybe a little bit more of neurobiological lecture this time, but anyway we will consider certain molecular mechanisms. I'm not sure if today or tomorrow, that depends on how fast do we go through all these slides, but definitely we will. So first of all, let's start with the question of what is the sound. So that involves a little bit of physics. Well, we will not get deeply into that, but of course I need to mention something, because since we are going to consider some sort of biology of experiencing different sound, you will definitely want to have, first of all, some sort of definition of what is considered a sound. So first of all, sound is a vibration that propagates as an acoustic wave through a transmission medium such as gas, liquid, or solid. So you may have sound waves in any of these media. Sound is transmitted through gases, plasma, and liquids as longitudinal waves. So that's a longitudinal wave. So nothing moves in the direction that is perpendicular to the sound wave, so only along the direction of wave propagation. And it is called the compression waves. Through solids, however, it can be transmitted as both longitudinal waves and transverse waves. So there are some options. Here in the right corner you see some sort of example of sound wave propagating through media. What is interesting here, you may consider different particles here, and you see these particles are more or less something like wobbling. I guess this medium, that's something more like a fluid, because in gas you will have all these particles moving around pretty fast, but despite the fact they are moving fast, they don't go very far from the position where they started. That's because they have some enormous number of different collisions, and all that moving around just gets them nowhere. So they approximately stay at the same point, but they move pretty fast, and they have a lot of collisions. So this is more like some sort of fluid. Particles are not trying to move so fast, and here you see that they are somehow wobbling here and there, and here you see the sound wave that is propagating through this media. So that may be interesting for you. So here is an example. You have some sort of speaker, and here you see the speaker is generating this sort of sound waves. So it generates some compressions and rarefications of the air, and they are propagating. And here you see that some, I don't know, some visuals for different terms like frequency. So here you see some low frequency and high frequency waves, and here you see intensity, like low intensity and high intensity waves. Sounds that are perceptible by humans are from 20 Hz to 20 kilohertz. That's 3 orders of magnitude, so that's really impressive, because you basically from 20 to 20,000, that's really impressive, 3 orders. And the wavelength are from 17 meter to 17 millimeter. So basically from, I guess, 1 to centimeters to 17 meter. That's impressive as well, especially if you take into account that the waves with such a large wavelength, they should diffract, and the diffraction of the waves should somehow stand in the way of perceiving them. And here are some formulae for you, just some sort of reminder how that looks like in some mathematical representation. What do I have here for you? Here I have a video for you. A, a pretty interesting method of
I'm going to show
visualization.
you the sound of a clap. And I don't mean some digital depiction of a clap. I mean that when this man's hands come together, you're going to see something that is normally invisible.
So here you see a method of visualization that is called, I guess, Schlieren photography, or here in this case that will be a Schlieren video. Uh, I'm not getting into the details how that's done. You can find many different videos on YouTube that show this method of visualization. It's used in technique, so some I don't know, some propagations of air, some turbulence, they are visualized with this sort of method. And there is even a nice video from Veritasium, or even more than one video that shows this sort of method used. So you can find that on YouTube. And what's interesting, Veritasium, I guess he failed to capture the sound wave with the Schlieren, let's say, video. But this guy was able to do that, and I guess we will see the result. So here is a clapping of hands, and here you see sound waves. Well, here he explains how this method works. I don't think we will get through all of these. All of the video, but most cases you see that some turbulences of the air, and they are visualized. Let me check. Yeah, here he shows the scheme, how that works. There should be a Schlieren knife. Let me check. Yes, so here it is. So here is the full scheme. So here you might check what happens if we have in here something that disturbs the air, and what happens to the light of that when it gets through that disturbance of the air. So here you see the plot. So some of the light gets blocked, some gets through, so you are able to visualize some changes in the of the density in the air. So here you see the heat of the hand is visualized, someone is sneezing, and so on. So there are many things you may want to visualize with this sort of method. Just one more thing to show you. This is not a sound wave. This is a blast wave. They are different, and there is a little bit different physics behind them both. For example, for the sound wave, you have something like constant speed of sound, and probably I have one or two slides that with that speed of sound. But for the blast wave, the radius, the growth of the radius of this wave goes something like time to the 2/5 or something like that. So you may check so-called Taylor formula for the blast wave. And here I just want to show you that sort of blast wave. It's not considered sound because a little bit different physics. It's not periodic. It doesn't have the constant speed, and so on. When of course when attenuated, whoa, something wrong with the YouTube. Okay. No. I'm sorry. As always, we are getting some technical troubles. Let's try again. Okay, should we wait for it to start? Okay, guess there is can I get at least some details? Okay, let's try. No, we can do even this. I don't know what's wrong with all these software guys. It's incredible. They can't even make a simple video to play. So here you see the blast wave. That's a slow motion, so this is not a real time, but I don't know, some maybe 100 of times slower or something like that. So here it goes once again. No, it doesn't go because okay. Okay, let's get let's get to another slides. So I'm sorry, but modern software, as you see, is good. So let's get back to the sound. So now we know that sound is periodic, so that's great. But periodic doesn't mean that it's simply some sort of sinusoidal wave. So that may be something much more complicated. So here you see some part of the wave along one period, and the interesting part is that when we analyze this sort of stuff, we tend to move to so-called Fourier representation, or perform some procedure, some mathematical procedure known as Fourier analysis. Did any one of you ever tackle with the Fourier analysis? I guess yes, but just in case. No? FFT algorithm. Okay. Then just few words. That's a method of representing any periodic signal in a form of sum of different sinusoidal waves. So you can take many periodic waves in forms of some sines, maybe cosines, that a little bit depends, but you can weight them with different coefficients, and adding everything together you get the final result, so the final signal. Here it is. And that's basically the basis of so-called spectral representation of the signal. So here is a spectrogram of some signals. So these are some sort of dolphin vocalizations. Here you see the 3D surface. That's a spectrum and time. So if you look for some time, you can take spectrum every second and draw this sort of let's say 3D plot. So probably you have seen these sort of spectrograms, especially if you have performed, I don't know, maybe some machine learning on sounds or whatever. They are often used as input features, so not just some bare signal, but something like this may be used. And here are examples of different spectra for some musical instruments. I'm not very familiar with them, but here are examples for so-called bass or carrier wavelengths for some notes, some music notes like G4, G5, so on. So here you see some spectrum for the flute. Here you see the spectrum for the violin, and different notes represented here as some sort of peaks. Except for the main tone, you have so-called overtones that, of course, you hear. And what's even more interesting, if we remove even the main tone, we leave only the overtones, our brains are capable of processing that and restoring the main tone even in the case of it's missing. So if the fundamental frequency is removed without removing the harmonics, we get the illusion of the missing fundamental. So the auditory system, it uses the pattern of frequencies in sound harmonics as a part of the perception of pitch. That was used throughout the history. For example, Fogler, an 18th century organist, applied this to create an illusion of the bass notes on a portable organ by playing only the higher harmonics. So he had some sort of portable organ. Of course, he couldn't carry some of the biggest pipes that give you that deep bass notes. But he found out that if he plays some higher notes, he can create the illusion of that bass notes just without them. I guess we can try. I have some demo here. I guess we can try to use it right now instead of sometimes later. Let me just check where do I have link for it, and I definitely do. Okay, so here's the demo starting. Okay, while it starts, I return back here. Okay, so here's our demo. That's a sort of demo that generates some sound with overtones. So I have some base frequency that I can define here. I have some number of overtones. I have some sort of attenuation, so these overtones, they are attenuated with the exponential law. And here I have some graphical representation of that. Here are basically two signals, one for the left ear, one for the right ear. Right now they are perfectly coinciding. I will show you why do we need that later when we get to some later slides, I guess even tomorrow. But this thing, let's check it today. I will try to start this, and you somebody tell me if you hear the sound, because I'm not sure if it is transmitted through Zoom. Okay, do you hear any sound or not? No, no sound. Okay. Does anyone know how to fix this, or some microphone mouse?
It might be when you can share only one tab, separate, not the whole desktop. It might work, but yeah, I know that works in Google Meet, but not sure for Zoom.
So it may not work here. What if I try something like stereo mix here? By any chance? Let's try. Anything? No. Okay, I guess that doesn't work. Good. Let me think. Okay, maybe I can try to reshare just one tab, but can I do it in Zoom? I'm not sure. Oh, it's here. Audio settings. Really wanted to show you something, but not sure how to do that. Was in advanced. Okay, so nothing I can find here. Good. Good. Okay, maybe you can open that on your own. So there is a link in our presentation. It's just a little bit far ahead, like slide 76 or something. Which one it is? Yeah. So slide 76, and you may check that on your own, and maybe before we have some lecture tomorrow, I'll try to come up with some idea what to do with that. The main idea is that when you start some sound, let's say 440, and you hear you hear some beep beep. Then you can check these box, like exclude the main frequency. So here you see how the FFT signal changes. So exclude the main frequency removes the sort of first peak. Oh. And the interesting part is that you still hear the same tone, whether it is or it's there or it's not there, or at least you hear something really approximate to that sort of tone. You may play around with different frequencies and see where it works, where it does not work. So at some point you will hear that something is really missing. Works good for some low bass frequencies. If we have some high bass frequencies, it's not so good. I don't know, maybe 10,000 still. Oh. So you can still hear that, but excluding the main frequency just leaves you with nothing, and so on. So you can check that, and I will come up with some idea how to show you this thing tomorrow on the tomorrow's lecture. Good. Okay, so just a few more notes. That's regarding the velocity of the sound. In many cases, like ordinary temperatures, frequencies, more or less well-known gases, we can approximate everything with the ideal gas and consider the sound process as adiabatic. So that means there is no heat exchange during the compression. Once again, if you have studied some sort of thermodynamics, you should know what that is. Well, without getting really specific into the details, here you see some formula that shows you the dependence of the velocity on different parameters of the gas. So here you have some adiabatic index like gamma, and here you have all these parameters like temperature, some molar weight of the gas, and so on. What should we note here? the interesting part is that we have this sort of molar weight of the gas involved. So if you take different gases, you will have different velocity in that gases, just due to the fact that some of them are heavier, some of them are more lightweight. If the gas is more lightweight, you have these parameters smaller, so you have the velocity what? Bigger or smaller? So if this m goes down, the velocity goes up. Absolutely correct. It goes up. So here we have it. You might wonder why it's interesting. So here's an example for you. Depending on the velocity, you will have different frequency, different main frequency for a resonator, so different resonant frequency. And here are some examples of different velocities calculated for air, for helium, for hexafluorous sulfide, and so on. And you see that the resonant frequency linearly depends on that velocity. What does it mean? There is at least one resonator that we carry around with us all the time. That's basically our, let's say, system for vocalization, so for speaking something. And this change in the molar weight, in some cases in the gamma, because that depends on the number of free I forgot the word how it's called, so gamma may change depending on the number of atoms in the gas, and you get different numbers. These different numbers lead you to different resonant frequency, which means that you have different sounds with the same resonator. And that's the reason behind if you breathe something different instead of air.
I promise to show you something really cool as long as you promise not to.
Once again, the question: do you hear this video when I started? Do you hear any sound, or it's not working as well?
To show you something really cool as long as you promise not to try it at home. Okay? Okay?
Did you hear anything? No, there is nothing. Okay, what if I try to turn off my headphones? Let me try to turn them off, and I will try to crank up the sound and turn it on like this.
As long as you promise not to try it at home. Okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
Well, several factors is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that.
Although this gets really long, although somehow I'm still funny. It's scientific!
Okay, I hope that you heard all these all this part of the show. Yeah, because this time we have the same microphone getting my voice and picking up loudspeakers. Okay, let me return back to the headphones. So that's basically the reason behind voice sounds funny or somehow different, like a rock singer after you breathe some different gas. The last thing to notice, here you see the difference in the pressure that is basically caused by sound wave. So sound wave, it's causing some changes in the air pressure, and here you see this P sound taken into account in the equation. And here you see that we are really sensitive to the sound, because even at painful, nearly damaging sound levels, the density of air changes just by something like 1%. So here you see this sort of table. These are decibels. We will see them in some next slides. There are a few formulae for you. And here is the pressure. So you see that compared to the atmospheric pressure, that is 10 to the 5 Pascal, even the 2000 Pascal, that's a jet engine, 160 decibels, that's almost nothing. So our hearing is very, very sensitive. So that's the take home. And these slides, that's just some sort of showing you that the measured sound velocity may be a little bit different. That depends on the humidity, depends on many different parameters. So these are just some sort of numbers for you. So here you see that molecules are moving really fast, like 500 meters per second. The speed of sound is around 300 meters per second. But it's not the molecules carrying it, but differences in density are carrying that sort of information, so that sort of sound. And what's interesting, that molecules are diffusing very slowly, sort of something like 0.5 millimeter, I guess, per second. That's because the enormous numbers of collisions, like 7 times 10 to the 9th. So that's what we have. So you might you might check that numbers later. Good. Sound intensity. So you see that we need something to measure the acoustic intensity, or we may call it sound power intensity. That's the power carried by sound waves per unit area in a direction perpendicular to that area. May sound a little bit obscure, but there are many such quantities in physics, so you will probably get used to that when you make some more get into some more details. Here are some formulae. So that's a sound intensity level, or acoustic intensity level, short and seal. That's a logarithmic quantity, can be measured in pairs, in bells, or decibels. Most cases I have seen decibels, and I'll be honest with you, never have seen any of these two. But they are related pretty simply to one another, so it's not a big deal actually. So here you have the formulae. So that's how do you calculate the intensity in pairs, in bells, and in decibels. So this is not some sort of multiplication. These are just units of measurement. So dB means just you get the number that means decibels. I0 is some sort of auditory threshold. That's approximately the quietest sound a young human with undamaged hearing can detect at 1 kilohertz. So here you see the exact number. So we are just using this sort of number, and it is supposed that if we are on this sort of threshold, like I equals to I0, we should get 0, because I0 divided by I0 gives you 1, and logarithm of 1 is equal to 0. So sound intensity will be 0 at the threshold level. The acoustic intensity is proportional to acoustic pressure effective squared. So here you see this number. So this intensity is proportional to p squared RMS. So that's when you integrate the pressure squared during I don't know, one period, and then you divide that by that period. You have probably seen that if you have ever studied electricity, you have seen these sort of numbers with respect to I don't know, current, for example, or some voltage and so on. And it is divided by Z0, so here it is, that's impedance, I guess. The sound pressure level or acoustic pressure level is a logarithmic measure of the effective pressure of sound relative to a reference value. So here you see a different value. Once again, it's calculated like some sort of logarithms of something, but this time you take the pressure instead of intensity. So here we had intensity, here we have pressure. So depending on the situation, you may use one or another, whatever you need to calculate. So that depends. Here you have these sort of plots that show you some sound wave. So here you have some sort of sinusoidal wave, and here you see the calculation of that root mean square of the pressure. So here you see the formulae, so you are like integrating the square and you are dividing by the length of the period, and that gives you some sort of mean value. So here you see the sinusoidal wave, here you see the square of that sinusoid, and here you see the PRMS. So when you make everything even, you calculate that sort of mean value. The interesting thing that if you know the form of the wave, you can calculate this integral, and it turns out that that's the peak value for the pressure divided by square root of 2. That is approximately 1.4. You have probably seen this formula where if you were ever dealing with electricity. So you know that we have 220 volts in our socket. So if we are using any electric appliances, there will be written somewhere 220 volts, and these 220 volts, that's actually the RMS. So that's effective if you take that sinusoidal wave, you square it and do all these things, you have 220. The peak number in the regular outlet that you have in your apartment is higher by square root of 2. So you need to multiply 220 by 1.4 and you get something around 380 or something like that. So I can do that multiplication in my head, but if you use some sort of calculator, you'll get the exact number. So here is pretty similar situation with this sort of pressure wave. Here is another interesting thing. So as the sound waves, as they spread around, well, if you study the some sort of physics, you will meet different forms of the waves, so on and so forth. But probably the most simple and the most interesting, I guess, is the spherical wave. So the wave that goes around some point source. So here you have some source, and the wave is just spreading around, and you see that the energy of this wave, when you are getting further and further from that source, will be spread around a sphere that is larger and larger and even larger. So some very, very large sphere. And the area of that sphere, of course, that grows as the square of the radius. So you know the area of the sphere, like something like 4 pi r squared or something like that, and the main component is that r squared, so you have some square. So if you measure anything on different distances from the point source, you will get like different numbers, and these numbers should they depend on one another and increase and decrease as 1 over distance squared. Here are different devices to measure a sound level that you can use and that were used previously. So here is some sort of sound level meter. This one is pretty old one. That's from 1962. Arguably the first portable sound measurement device. Weighs something like 5 kilogram, and also the level recorder was another 25 kilograms. So heavy device. Today you can use any of these, so you can have some portable measurement devices. You can even use your phone, so it's not very reliable, but more or less it can measure something. So even your phone can approximately handle the problem. And here is some sort of sound level monitor used in different factories, and this one even shows you whether the level is good enough, let's say, to continue working on the factory, or you should immediately leave that place because you may get some damage to your ears. Of course, we have some sort of standards. So here you see once again the table you have seen with decibels and different sources of the sound. And here you see some sort of safety precautions, so which levels are considered to be okay and where we are, let's say, not okay. So if you have these dBAs like 85, you can work there for 8 hours. But if you get to 88, only 4 hours are allowed. And there are some sound levels where your ears will last for something like 1 second. So that's that's pretty possible, and that's not the highest possible level. The loudest sound that has ever been measured by humanity is considered to be the explosion during 1883 eruption of the Krakatoa. So that was somewhere between May 20 and October 21. And the interesting part is that this thing started as some sort of blast wave. So blast wave is not sound. So it started as a blast wave, but when it gets pretty far around, it gets like smeared over that large sphere. It is transformed into a regular sound wave. And that sound wave, it was registered on the, let's say, pretty far away from the place of the eruption. So it was heard something like 3,000 kilometers away in Perth, Western Australia, and the Indian Ocean island of Rodrigues, 4,800 kilometers away. So that's really, really far away. That was really noisy. The loudness of the blast here to 160 kilometers from the volcano has been calculated to have 180 dB SPL. Some sources, you may find in some sources, claims that at the epicenter you had something like 310 decibels. But the thing is, it's impossible. You cannot have this sort of thing. And how do you think why? Let me give you a tricky question. Why do you think we have some sort of upper limit for the maximal possible sound level? Let me even help you. I will find formula. This one or previous is better.
Maybe some particles will interfere and won't be able to break through.
You see, we have the pressure of the sound like added with the atmospheric pressure, but pressure of the sound is periodic. Yeah, so you have some additional pressure and you have some rarefication when it is, let's say, subtracted from the sound pressure. So here so it's really good seen in this image. So you have some mean density of the particles, and when the wave goes, it in some places it adds to that density, so it increases the pressure. In some places it takes from that density and it decreases the pressure. How much can we decrease the pressure?
No more than to 0?
Yeah, so no more than to 0. So if we are living in the world with 1 atmosphere of pressure, so 10 to the 5 of pascals, you cannot get lower down than 10 to the 5 pascals. You get to the perfect vacuum and that's all. So we have some cap for the pressure of the sound wave that is equal to the atmospheric pressure. Which means that when we calculate these sort of things like P sound over P atmospheric, or if you calculate something like this, so these P RMS, we will not be able to exceed some threshold. So if we have some sound that's, I don't know, some sinusoidal wave of the sound, this P peak cannot be larger than the atmospheric pressure, because we will be subtracting it from the atmosphere and we cannot get lower than 0. So that's the reason why this PRMS has some sort of cap, and using this cap on the PRMS, you will get some number that is basically the maximal loudness possible. That's 191 decibel. So yeah, I'm not showing you the exact calculations, but you will have to do something similar at home. Yes. So that's for you to notice that we have some cap. It is caused by the fact that we cannot have pressure lower than 0, so the amplitude of this sound wave cannot be larger than the atmospheric pressure. So that's the reason. Good. One more thing to notice, since we are going to deal with some sort of human perception, you see that we are perceiving different frequencies differently. And what to do with that, to measure that somehow, we should somehow correlate how do we perceive these frequencies. And you see that the phone is a logarithmic unit of loudness level that is equal to the sound pressure level of a 1 kilohertz pure tone that is judged as having the same loudness. So you see this word judged, which means that we are hearing one sound, we are hearing another sound, we are matching them as we think the most closely, and then we measure what really happens with some sort of physical devices, and we have that physical numbers and their perceptions, they are non-linear. So thus we have these sort of different curves. So an equal loudness contour is a measure of sound pressure level over the frequency spectrum for which listener perceives a constant loudness when presented with the pure steady tone. So here you see two different kinds of curves. One is more recent, the other was the curve first developed by Fletcher and Munson, and they are, I guess, more of some historical value. And that's basically the plots that we have. Some parts you see are estimated, some parts were more or less measured. So if you listen to music with vocals, basses and high-pitch instruments, and you lower the volume, the vocals will become relatively more audible. So that's one of the reasons for that, this sort of non-linearity in our perception. And here I have shown you the part where we create sounds. So we hear a pretty large set of sounds. So frequencies from 20 to 20,000, while our speech, so the sound that we create, they lie somewhere between 1,000 and 2,000 hertz. So here it is. Of course, these devices are used in medicine. So here you see some sort of audiogram. Here this guy is assessed. So how good does he hear on different frequencies, and depending on his hearing, on that results, you might say whether there are some problems with ears or with hearing. So that's performed with the help of the audiogram. It's often measures something like 6 to 8 different frequencies, ranging from 250 to 800 to 8,000 hertz. And here is an example of the plot for you. Of course, different animals may hear different ranges of sounds, and here you see first of all different sounds classified and how that's used in technique. So below 20 hertz you have infrasound, so here we have acoustic, here you see some low bass notes, here you have ultrasound. Some animals operate in these closer ultrasound region. Here we have some medical devices, so probably you have seen that ultrasound devices, and over 2 megahertz you have some sort of diagnostic devices as well. Here is a table for you. These are different ranges of hearings for different animals. You may find humans here, you may find bats. The thing is that many insects like moths and beetles, they have good ultrasonic hearing, and most of these are nocturnal insects listening for the echolocating of bats. So upon hearing of bat, some insects will make evasive maneuvers to escape the bat. So here you see that. Interesting thing that cats are trying to listen to rats, and they are that sort of evolutionary arm race when one is trying to get to some, I don't know, some higher frequencies, so to be not audible with the other, while the other is trying to adapt and get into a bit higher frequencies than the first one. So I guess you can check this sort of table. Interesting part that dogs can hear for some ultrasounds, and here you see a dog ultrasonic whistle, like silent whistle or called Galton's whistle. This is the same Galton, if you maybe know, the Galton board or regression toward mean. That's all the same Galton. And you may check this table. Maybe you will see something interesting here, like say the smallest range is, for example, for the chicken. So here you have 125 to just 2000 hertz. The largest range, I'm not sure. Maybe beluga whale from 1000 to 123,000. So you can check that and find maybe something interesting for you. And here are different cases when all these sounds, especially ultrasounds, are used. So for, let's say, echolocation in bats, so they are capable of maneuvering in complete darkness. We use them for ultrasonic, for obstetric ultrasonography. So here is a prenatal ultrasound. Whales use it for echolocation. So here you see one of the examples, so how that works. Here you see some sort of lens created by different tissues, and it focuses in some appropriate way this sort of ultrasound, and then when the echo comes back, it is received, and they get some information that there is some fish. Whale use for communication different low frequency sounds, like from 10 hertz to, well, they use very large region of the sounds, but as far as I know, they may use quite low sounds like 10 hertz, and they can be heard pretty far away, especially in the sea. Some elephant communication, for elephant communication they use sounds from 15 to 35 hertz. That's really really low pitch sounds. Good. So we have gone through a little bit of physics for all of that things, and I guess now we can get into a little bit of biology. How do we register different sounds, and then we will get to how do we process them and so on. Today I'm planning to get, I guess, through the anatomy of the ear, and maybe you will get some interesting insights or something like that. So here you see the human's ear. You see it can be subdivided into the outer ear, middle ear, and inner ear. We will get through them one by one. Here you have the pinna or auricle. You see it has pretty interesting form, and each part of the pinna, it has its own name. Maybe I'll tell you a little bit later why do we need some sort of complicated shape that has to do with the localization of objects in 3D, especially it has to do with the height of the sound. So in a plane we can localize it good, but if we need to localize how high is the source of the sound, it has to do with this sort of thing. So probably if you somehow cover some parts of your ear or something like that, you should get some troubles localizing objects with respect to the height of the object. So that should be perceivable. Maybe we could have made some sort of experiment if we had offline classes, but you can try that at home, I guess. Good. Here is for comparison. Here are ears of the cat. Once again, we have pretty similar structure. We have some outer ear, we have some middle ear, and we have some inner ear. So they are pretty similar, and if you understand how one works, you definitely get how the other one works. The middle ear contains, I guess, the smallest bones that we have in our body. So here's an example. You see somebody is just carrying them on a finger, so you might guess how small they are. Of course, they have their names, so these ossicles, they have certain names. And the interesting part is, I guess, oh, that's too far, or do I have it? I want some image. No, let me return back to this image. And how do you think, why do we need this sort of strange contraption in our ear? So here you see that the tympanic membrane. This tympanic membrane reacts to the changes of the pressure. So we have some changes in the pressure caused by the sound, and these changes of the pressure are transmitted to this sort of thing, to the inner ear. Here you have some sort of oval window. Inside there is a liquid inside, so that's a really big hint for you. So there's a liquid there, and these bones are pressing towards that liquid. And here is another interesting
sound.
I'm sorry, I didn't hear.
It just amplifies sound because the vibrations are transmitted easier using the dense environment.
Probably yes. I guess you mean the thing that I think. If we have two different environments with different densities, it's really hard for a wave to get from the environment with lower density into the environment with higher density. So that's a real trouble. Let me show you first this sort of image. So here you see some sort, that's not a wave but some peak is getting to here, and here is the border, and that's the border between two environments. So this environment has higher density than this environment, and you see that the part of that wave, it gets some scattered, gets reflected back, so you get some reflection, and the more reflection you get, the worse is the situation, because the less energy gets through and is able to cause, well, something in there. So you will have some detectors in there to detect that sort of wave, and of course you want the most of the energy to be transmitted, so not reflected back. And the maybe I guess I have a video here that should probably show this case. I hope that's it.
Here's the live version of this demonstration. Notice that when the pulse goes from a
So
low
here you
density
see,
medium to a high density.
Here you see what happens. So this part is showing you environment with low density. So this spring shows you environment with low density, and this spring, that's environment with a high density. Yes, some part is transmitted, but some part you see is reflected back. So the thing is that if we didn't have all these all that system, the sound wave would have a lot of troubles getting into that liquid environment from the air. So most of the energy will be reflected back, and you will get almost no energy in there, and you will have troubles, of course, detecting that sort of thing. So you need more energy to be transmitted. So that's the reason for these ossicles to exist. So here you have a tympanic membrane, it vibrates, it has air on the both sides, so that's not a problem. And here you have ossicles that are trying to push towards the liquid, and now you don't have some direct movement of the sound from the environment with low density to the environment with the high density. And the thing is called the impedance mismatch. So these ossicles, they act like levers, so the that small movement becomes a larger movement of the stapes, and this movement is transmitted inside, so you are matching the impedances of the two environments. This thing is used in technique. So here is an example from optics. I have shown you these, I guess maybe even this exact image in the first lecture when we were considering some sort of quantum mechanics, and I told you that we may have some effects that help us alleviate the problem of reflecting the light back. And here you see two images taken with and without this sort of technique when we are trying to match the impedances and get more energy inside. So you see this photo is much better than this one. And here is another example. So that's an ultrasound performed, and here you see this sort of slimy liquid. If you have ever seen or you were in the you have seen that ultrasound, you know that doctors are using this sort of thing. So why do they use it? Because if you have just this sort of device, the ultrasound gets into the air, and then it will need to get from the air into the patient's body, and you have some massive amount of reflection on the border between air and patient's body. so you don't get, you will not get a lot of that ultrasound in the patient, so you probably will not have some good readings. So you need this sort of liquid to match the densities. So that's why the ultrasound is basically emitted into the into this sort of liquid, into this environment that has some much larger density than the air, and then it has little trouble of getting inside into the patient, and so you will get some nice clear readings in your device, not just some sort of everything messed up and scattered all over the place. So yes, that has even some applications, as you see in medicine. These same physics, but you see different, let's say, directions. So something we have applied in our biology, something is applied in medicine, something will be applied somewhere else. Good. Let me just check for a moment. Where are we? Because I start feeling that we are scarce on time, and I want to know how far. We need to get here. Okay, I'll try to do that quickly. So yes, so here you see these oscillons as the system of levers. So I'm not getting into details, you probably know how that works. So here is one more example. So here you see once again all the oscillons. Here you see the oval window, here you see the round window. It is needed. Here is the cochlea, because that's that thing around, it's basically a bone and it's not stretching, and these windows, they are stretchy. Please note that you will have for homework question, why do we need this round window, so you may think about it. Of course, if we have some organ, we have certain troubles with that organ, and here you have some list of possible impairments that we might have. Some conductive hearing impairment, that may be autosclerosis, or that's some growth of bone in the middle ear that interferes with the movement of the ossicles. Some temporary conductive hearing loss can accompany inflammation in the middle ear, so like otitis or something like that. Another common cause may be some cerumen or earwax. Of course, there may be many other reasons, like sensory neural hearing impairments that due to damage to the cochlea, to auditory nerve, or auditory areas of the pathway of the brain. We will get to that areas at some point, and you will probably get to the idea. Many people experience tinnitus, so that's from Latin tinere, to ring. That's perception of the sound in the absence of that sound. Here is example of that tinnitus, but since you don't hear what's happening on these pages, I will not run it. You can check that later, just using this sort of presentation. Of course, there might be some troubles due to noise-induced, some noise-induced hearing loss. Can be temporary and reversible, or it can even be permanent, depending on the noise level and duration. And you have even seen some sort of industry standards for the noise levels, so that people don't work into some really bad environment. There may be some other troubles, so some mechanical damages. There may be some problems with, let's say, excitotoxicity, so and some other biochemical problems, some overproduction of the oxygen-based free radicals. We probably heard about ROS, so reactive oxygen species, that has to do with that. So many troubles can be. Of course, we have some changes in our perception of the sound that are connected to our age. And here you see pretty interesting plots that's patterns of hearing changes in women and men from denarians to nonagenarians. So that was performed, the study was performed in Japan in 2021. 10,000 Japanese men and women between ages of 10 and 99 years all were ear disease free, so that's in case if you don't have any additional disease. And here you see the changes of hearing threshold depending on the frequency and on the age. So you may want to check these plots later if you want to know what will happen with all of us when we get older and older. Good. Let's get to the well, actually we were in the middle ear, but let's look at it more closely. So here you have once again these ossicles like malleus, incus, and stapes. Once again the foot plate stapes at oval window, so here you see that. Here you see the cochlea. Here you see the tympanic membrane, the auditory canal that gets from the outside to here, and from the inside you have the Eustachian tube that makes the pressure even on the both sides of the tympanic membrane. So here we have two little muscles, the stapedius muscle and the tensor tympani muscle. They are both attached to the wall of the middle ear at one end and to the ossicles on the other end. So here you see one of them and here you see the second. So when tympani muscle and the stapedius muscle contract, the chain of ossicles becomes much more rigid and sound conduction to the inner ear is greatly diminished. The onset of a loud sound triggers some neural response that causes these muscles to contract, and response is called attenuation reflex. So we have that. The problem is that this reflex has some large delay, like 50 to 100 millisecond, which mostly means that damage was already caused and nothing can be done. So why do we still have it? I'm not sure, but maybe there are some reasons. So once again a little bit of of anatomy. So here we have the bony labyrinth. That's a hollow structure within the petrous portion of the temporal bone. Within it lies the membranous labyrinth, which contains sensors for both the vestibular and auditory systems. I guess we will consider both of them. The membranous labyrinth is filled with endolymph that is sodium poor and potassium rich. We will consider why do we need that sort of composition a little bit later. And surrounding the membranous labyrinth, in the space between the membranous labyrinth and the wall of the bony labyrinth, is so-called perilymph. So it has pretty different composition. So you see the photos here and the scheme you see here. So here is our oval window, and that's basically the different details. Once again, all these details shown here. So here you see some parts of it, like a spiral. So here you see some ganglions, you see these helicoderma and so on, and here you see some cut. So how that looks in such a cut through. And we will be interested especially in so-called organ of Corti, because that contains basically the cells that convert sound and changes in that pressure into some electric pulses or some action potentials that are fired with by the neurons. So we will consider that in much more details as we go through these slides. Here you see once again that sort of cut through. Please notice here we have endolymph, high potassium, low sodium. Here we have perilymph, low potassium, high sodium. Here is the organ of Corti, and here will be certain cells that have access to both of the endolymph and to the perilymph. So they are these two lymphs, they are separated, but there will be cells that have some access to both of them, and they need it. So here you see the three scali of the cochlea, so viewed in cross section. The cochlea contains three small parallel chambers, and these chambers, the scali, are separated by so-called Reisner's membrane and the basilar membrane. So here you see the Reisner's membrane, and here you see the basilar membrane. And the organ of Corti that performs the work, that contains auditory receptors, it sits upon the basilar membrane and is covered by tectorial membrane. So here you see the tectorial membrane, and well, there is certain interesting point that ionic concentrations, they differed very much, and the permeability of Reisner's membrane, the endolymph has electric potential over 80 millivolts. It's called the endocochlear potential. So we will get to the point where do we need that and why it's done so. So here you see once again different cross sections, and here we are getting to the here you see that organ of Corti, and here you see the bone around the bony structure around the thing. You see this bone has some sort of holes, and the liquid can get through that holes. So it's really crucial. So the holes in the lower shell of the osseous spiral lamina, they were named the Kneculi perforantes Schuknechti. And here you see, if you are trying to stain, I guess that's staining for acetylcholine esterase, you see that it gets to many different places. So staining solution from the osseous spiral lamina through the habenula perforata into the organ of Corti. So it gets even to the organ of Corti. And you see these cells, they are washed around. They are washed around with the lymph that is able to get through that channels. And from the above, there is a pretty different lymph with a very different concentration of the ions. So here you see this organ of Corti. Here you see the endolymph from the above and perilymph from the below. And they are in the perilymph and in the endolymph from the above. And that will be pretty crucial for their functioning. I guess I will show you that later. Good. Where are we once more? I guess we should be almost. Yes, we are almost there. I guess we are even. Whoa, we are even a little bit ahead of schedule. That's incredible. Good. Good. Now let's get to the a little bit even closer to the detection of the sound. We need not only detect that there is some sound, but we need to detect different frequencies of that sound to make some sense of it. So if we were just detecting the absence or that there is some sound, it will be no much information for us. So how do we do that? So here you see once again all these anatomical structure, and here you see the cochlea is unveiled or uncoiled, if you wish. So here it is. That's some sort of thought experiment. So of course you cannot do that in practice because it has all that bony structure around it and so on. But if you imagine that you do that, you can probably draw it something like this. So here you have the stapes, here you have oval window behind it, here you have the round window, here you have the perilymph, and the basilar membrane. So here is the basilar membrane, here you have all these all the things. If we return, I guess, to where do we return? So here you see these sort of where do we return? We return to here, for example. So here you see the basilar membrane. So this is the basilar membrane that we will be considering. So here's the Reisner's, here is the basilar, and here is the organ of Corti. Okay, so here you can see once again organ of Corti. So here you see all that bony structures, and here you see the basilar membrane and Reisner's membrane, and here is really small the tectorial membrane. So all that stuff. Do we have? Yeah, we have one more image here, so a little bit closer. So here you see once again the basilar membrane, the organ of Corti that is based on that basilar membrane, and you see all the other structures. You see this bony structure, the nerves are getting inside through this bony structure, and they are connected to specific cells. We will consider the cellular level tomorrow, I guess, and here you see all these details. So if we schematically like unravel everything, like uncoil it, we see this sort of membrane. We know that this membrane is wider at the apex than at the base by a factor about 5, and its stiffness decreases from the base to the apex, and the base being about 100 times stiffer. So the thing is, so when the sound pushes the footplate on the staples at the oval window, the perilymph is displaced within the scala vestibuli, and endolymph is displaced within the scala media because Reisner's membrane is very flexible. The wave travels up the basilar membrane, and it's similar to the wave that runs along the rope. So that video I have shown you with that sort of coils, so it may be applicable to here as well. So some wave running along the coil. So here you have the image how that happens. You see that these liquids, they are connected. So here is so-called helicotrema. At the apex you have helicotrema. So when you are pushing on the liquid from this side, this liquid will go all the way here through the helicotrema and go back to the round window and push on the round window. So this round window, it will bulge. So that's what we have. But the thing is that different parts of the membrane, they have different natural frequencies. And that's why if you have sound that is a combination of different frequencies, different parts of this membrane will respond and will displace by some larger or smaller amount. So here is an example. Once again, the thought experiment, we have something unraveled, and here you see different parts of the membrane. They are, let's say, sensing different frequencies in some sense. Of course, that's a little bit approximate, first of all. The second, they are good at sensing up to a certain point. So here you see different frequencies and how the membrane responds. So at 25 Hertz, so here you see the shape of the wobbling membrane in the lower and the upper positions. At 50 Hertz, the peak travels a little bit back, at 100 a bit more back, so on, but after 800 Hertz you see that it's almost without changes survives to up to 1600 hertz. So we have different methods of estimating these sort of different sounds, and we will get to that in the next lecture. But I just want to show you that we have something from the membrane, we have some information, and we will get some additional information, and that will be combined in our brain to get the information on the sound. And this is the last slide I want to use in today's lecture. That's an experiment that probably should convince you that it has sense for different parts of the membrane to wobble more or less vigorously depending on the frequency of the sound. So you shouldn't think that if it is some sort of rigid membrane, everything is connected, you can do that. No, that's pretty possible. And to show you that, here is an experiment when you have one device, but different parts of this device have different natural frequencies, and they will respond to different frequencies from the outside. So here let's take a look. So here we have one resonant frequency, one part of the system is resonating while the other are doing nothing. Here you have another frequency. Now this part is resonating while the other two are doing nothing. And here you see the last part is resonating while the other two are doing nothing. So you can make one part of the system resonate while the other just sit and do almost nothing. So that's pretty okay. And here is an example that has more to do with our ears. So here you see the wave traveling along that membrane. I guess I need a little bit change positions of this video. Yeah, let's bring them closer. Good. So you can see them a bit better. So here is high sound frequency. So you see some part of the membrane has reacted to exactly this sort of frequency, and here's another one. So another part of the membrane has reacted to the frequency. Or I have messed up and inserted the same video twice. That may be. Okay, I guess with that being said, we can complete the today's lecture. If you have any questions or comments, please fire away. Okay, no questions, no comments. Good, then have a nice evening and see you tomorrow.